All right, thank you all very much for coming. So we're really excited to, I'm really excited to talk a little bit about Micronaut, a framework we've been working on for the last about a year now. So let's get right to it. So my name is Jeff Brown. I am the co-founder of both the Grails and the Micronaut framework. How many folks here are familiar with the Grails framework? Lots of folks. That's fantastic. Has anyone done anything with Micronaut yet? All right, we're gonna. I see some hands in the back. Very good. We're gonna change some of that. As I said, I'm one of the co-founders of the Grails and the Micronaut frameworks, and also the Grails and Micronaut practice lead at OCI. So those are the same team, by the way. The Grails team and the Micronaut team are the same folks. The same tech lead. Graham Roche is the tech lead of both projects. Same folks, same company. So we don't have two separate teams managing these frameworks. And one of the great things about that is as we've started building Micronaut, we've been able to leverage a lot of the stuff we've learned over the last decade while building the Grails framework, and that's been a big help. So I co-authored a couple of the Grails books for A-Press, and you can find me on Twitter at Jeff Scott Brown. So OCI, of course, is the home of Grails and Micronaut. And we're based in St. Louis, which is where I happen to live. We are a distributed team and a distributed company. We've got folks all over the country and elsewhere. We've got folks in Spain and Australia, and so we're a distributed team. But our headquarters is in St. Louis, and as I said, that's where I happen to live. And one of the things that's interesting about OCI is training is a big part of our business and has been since the very beginning. So the company was founded in the mid-90s. And training's been an important part of what we do the whole time, and still is. We trained over 50,000 folks, and we've got more than 100 courses currently active in our catalog. And one of the interesting things about our training practice is we don't have any professional instructors. So all of our instructors are experienced practitioners with whatever the technology is that they're teaching. So for example, I teach a lot of our Grails and Micronaut courses. Training is just one part of what we do at OCI, I would love to talk to you about OCI. If you've got any questions about what we do, I'd be happy to, I'd be enthusiastic to talk to you about some of that. But I want to press on and get right into the technical content for the night. So I'm going to talk mostly about Micronaut, and I'm going to start with a little bit of history as it relates to the Grails framework, and press into that in as much as it relates to design decisions and things that have affected what we ended up building as Micronaut. So I'm going to start with a little bit of history and talk about some of the challenges that relate to some of that history and what we've done to address those challenges. And we'll take a look at Micronaut and hopefully get some folks enthusiastic and excited about the work we've been doing. So as I said, I'm going to start with a little bit of history. So the Grails framework is more than a decade old at this point, which is fantastic. So in February of 2008 is when we shipped Grails 1.0. And Grails predates 1.0 by about a year and a half, maybe a little bit more. So the framework is well over a decade old. And it's still very vibrant, still very relevant, and still an important part of our industry. And we're very excited and proud of that fact. Around the time that we started building the Grails framework, so remember the time frame here, 2006, 2007 is when the development really started on the Grails framework. Around that time, there were a lot of frameworks trying to emerge. A lot of folks were trying to build JVM web frameworks around the same time. And the reason for that is kind of the state of the art at the time would have been Struts 1. And Struts 1 was definitely an improvement over what predated Struts 1. It's definitely a better approach than implementing servlets yourself and implementing do-get and do-put and all that crazy stuff. But it was quite tedious to do simple things. You had to wire together several things. It involved quite a bit more code than it seems like it needed to, more configuration than most folks were happy about. And the framework didn't cover a whole lot of ground. So it was obvious there had to be a better way, and it was obvious to a lot of folks. So a lot of folks started trying to build web frameworks around that same time. So many so that when we very first started talking to people about the fact that we were going to build a JVM web framework, I was routinely asked, do we really need another JVM web framework? Because there were so many of these trying to emerge around the same time. And we didn't want to build just another JVM web framework. We wanted to really build a better way and really change the way that folks build JVM web apps. And I think Grails has been really successful at doing that. And a big part of the reason that the framework has been as successful as it's been for as long as it has been is the fact that the framework has evolved considerably over the years. Grails 3, which is the latest version of Grails today, is very different than Grails 1. So when Grails 1 was first being conceived and built, so think about 2007, REST is a good example of something that's changed a lot. So certainly the idea of REST existed in 2007, and people built REST services, but it was nowhere near as big and important as it is today. REST in particular I'm talking about. And because of that, there's not a whole lot of support in Grails 1 for publishing REST services. Certainly you could publish REST services with Grails 1.0, but you're going to be doing a good bit of the code, a good bit of the work yourself, right? You might have to write some custom marshallers for dealing with JSON and XML or whatever formats you wanted to work with. You might have to customize the data binder, content negotiation. There's a lot of REST kind of stuff that you'd end up writing a good bit of tedious code around, because there was not a whole lot of support for building that kind of app in Grails in the very beginning. And that really wasn't a deficiency or a gap or a mistake that we made. It reflects the fact that that was not important at the time, so the framework didn't prioritize features for building those kinds of applications. And then as REST got more and more important over the years, the Grails framework really stayed ahead of that by implementing more and more features that help people build those kinds of applications. And today in Grails 3, we've got fantastic support for REST. That's great. GORM is another good example. GORM is the ORM tool that's part of Grails, and it's been part of Grails since the very beginning. And initially, GORM was really conceived as a layer on top of Hibernate. We wanted to make Hibernate easier to use, take advantage of convention over configuration, provide some really interesting query capabilities that would be enabled by the Groovy programming language. We really wanted to make Hibernate a better solution for folks who wanted to use an ORM tool in a JVM web app. So GORM was originally conceived as that, a layer on top of Hibernate. And for maybe the first year or so of GORM's existence, one of the most highly voted feature requests was people wanted JPA support for GORM. They wanted to be able to pull Hibernate out and plug in TopLink or some other JPA implementation. Remember, the time frame is 2008, 2009, something like that. So we recognized that, and we refactored GORM to decouple it from Hibernate, and then allowed folks to plug in JPA implementation and still write mostly the same GORM code. So people were happy about that. And then fast forward a couple of years past that, and the so-called NoSQL databases started gaining momentum and traction and popularity. Databases like MongoDB and Cassandra and that whole gaggle of NoSQL databases started gaining popularity. And people wanted to use GORM with those kinds of databases. So we refactored GORM even further. And today we've got a whole bunch of really great implementations of GORM. So you can use Hibernate, you can use JPA, you can use MongoDB, you can use Cassandra, you can use Neo4j, which is a really interesting graph database. And there are others. But that's another great example of the technology evolving over the years to adapt to the way that folks want to build applications today, right? It wouldn't have made sense to have great MongoDB support in GORM in the very beginning, but it does today. So the REST story and the GORM story, and there are lots of other examples in the framework, but I'll leave it at just those two. Those are really good examples of the technology evolving significantly over the years to adapt to the way that folks want to build applications today, and that's been a critical part of what's enabled the technology to be as successful as it is for as long as it's been successful, and it continues to be successful. But that evolution is critical, right? If what we had today was Grails 1.0, it really would not be a terribly compelling solution for most folks, because the way folks wanted to build apps a decade ago is very different than the way folks want to build web apps today, right? So microservices represent another occurrence of the need for adaptation. Microservices is another good example of something that really wasn't terribly important a decade ago, but is really important today. More and more folks or enterprises are moving towards microservice architectures, and we want to address that. Grails, of course, is built on top of Spring and has always been built on top of Spring. So Grails 1 and 2 were built on top of Spring MVC, and Grails 3 is built on top of Spring Boot. And Spring does a whole bunch of really, really cool stuff. There's a lot of great value that the Spring framework contributes to developer productivity and code simplicity, and there are a lot of great things that the Spring framework has to offer. And those are reasons that Grails was built on top of Spring. But Grails and Spring both, really neither of them were really designed, certainly from the beginning, with microservices in mind. And they've both adapted over the years to be more compatible with microservices, but neither of these technologies were designed from the core with microservices in mind. And it turns out that limits some of our options while trying to use those technologies to implement microservice architectures. So microservices, just like the NoSQL databases and the increase in popularity of REST, microservices is another example of something that's changed in the landscape that we need to adapt to enable people to build those kinds of applications. So we have to decide what to do, right? So one of the things we could do is continue to evolve our current technology to be more and more compatible with the way folks want to build applications in 2018 and 2019 and beyond. Another thing we could do is we could go back to the drawing board and design a framework specifically for building microservices, and that's what we decided to do over a year ago. So the development of the Micronaut framework started about a year ago, a little bit more than a year ago, maybe just about a year ago. And one of the first things we had to do before we really started development was establish some goals. What are some characteristics that we want this framework to have? What are the goals for this endeavor? So we wanted to create a framework from the ground up, specifically with microservices in mind. Some of the attributes that we wanted this framework to have is we wanted to have really fast startup time, and we wanted to have small memory footprints, and we wanted to have small executable jar files, and have zero dependencies on other libraries. And some of these, and this is just a subset of the goals, of course, but these are some of the big ticket items that are easy to think about and easy to talk about. We had lots of goals for the framework, but as I said, these are easy to talk about. And some of these items sort of manifest differently in a microservice architecture than they do in a monolithic architecture. So think about memory footprint as a good example. A typical Grails application, depending on what it's doing and how well written it is, you might allocate, just say, a gig of RAM of heap to that Grails application. And maybe less, maybe more, but a gig is a reasonable amount of heap for a lot of Grails applications. For a monolithic web application, that's really not that big of a deal, right? In your development environment, you start the thing up and maybe you don't even think about it. You start the process up and you're consuming a gig of RAM and the thing is running, you're doing what you want to do, and maybe that's not top of mind. The fact that you're allocating a gig of RAM to that thing maybe isn't that big of a deal. There's only one of them, right? And in your production environment, the same thing. You just you set up your Tomcat or whatever server container you're using and allocate the RAM to that thing, deploy your application there, and you're off to the races. It's really not that. So the fact that you're using all that memory maybe isn't that big of a deal for a monolithic web app. But think about how that manifests or how that relates to a microservice architecture, where you don't want one of these things. You might want a bunch of them. Maybe you want 20 of them, or you want 100 of them. So in a microservice type architecture, think about your development environment first, right? So if you wanted to start up, you're not going to start up 30 Grails applications on your laptop concurrently. It's not practical for a number of reasons, and one of them is RAM. And the same with your production environment, right? So even though you could, and obviously people do, start up lots and lots of instances of say Grails apps in your production environment. If you're deploying to, say, a cloud environment where you're paying for the amount of cores or the amount of RAM that you're allocating to all these VMs, all that stuff starts to add up with microservice architecture. Again, because there's not one of these things, there's 30 of them or 50 of them or however many of them there might be. So some of these goals that we had for the Micronaut framework relate to things that affect microservices in ways that they they affect differently microservices than they do, say, a monolithic application. Startup time is another good example. So a typical startup time for a Grails application might be, again, it depends on what the application's doing and how well written it is, but say 20 seconds, put you in the ballpark, right? And we wanted much faster startup time than that. We wanted more like sub-second, 1 second, something like that. Not 20 or 30 seconds, but around a second. Whole different ballpark. So we came up with a list of goals. These are some things that we want this framework to accomplish. And then what we had to do with that list of goals was kind of map it to our current technology and make sure that we had an understanding of why can't we achieve those goals with our current tech. So why can't I run a Grails application in, say, 12 megabytes of heap? And why can't I start a Grails application up in 800 milliseconds, right? And all these goals we had to relate them to our current technology and figure out what is it about the current tech that keeps us from satisfying those goals, and that helps us figure out how to satisfy those goals. And for a lot of those goals, the equations maybe got a lot of variables in it. There are a number of reasons that we can't accomplish a lot of these goals, but a lot of it, certainly not all of it, but a lot of it has to do with Grails' relationship to Spring. So Spring, as I said before, Spring does all kinds of cool stuff, but it's expensive to get that really cool stuff. So one of the things that Spring has to do is it has to interrogate all of the classes in your Spring application context. It has to interrogate them at runtime. It's got to interrogate every class, every method in every class. It's got to do a whole lot of runtime reflection to figure out what all is out there and how do these things relate to each other and how does the dependency injection work, what needs to be injected into what else, what's transactional, what's cacheable, all the stuff, most of the stuff that Spring does relies pretty heavily on runtime reflection. And that runtime reflection is expensive. It's expensive in terms of performance, processor time, and it's expensive in terms of memory consumption. And to make it kind of worse in some ways is because of the nature of the problem gets worse as you've got more code, right? If the problem is having to search through all your code, then the more code you have, the bigger the cost gets. So that's, there are lots of details we could press into there, but runtime reflection was the source of, was one of the issues that keeps us from satisfying some of our goals with the Micronaut framework. So we really like the programming model that Grails and Spring have to offer, and those frameworks are great for building monolithic applications. We really like that programming model, but there has to be a better way to get the benefits of that programming model. And a good example of the programming model is think about the transactional annotation. So Spring has an annotation called transactional, and you can annotate a class with @transactional, and now all the public methods in that class become transactional. And what that means is when you call a method, a transaction will be started, and then the method executes, and when the method returns, the transaction gets committed, and if the method throws an exception, the transaction gets rolled back. And there's more details to it than that, but we'll say that that's enough detail for the point that I want to make. The fact that you can declaratively annotate a class with transactional and you get all this great behavior, that's the programming model that we really like. But the way that's carried out relies on a bunch of runtime reflection and stuff that has to be allocated, dynamic proxies, and the cost associated with that programming model is what we wanted to address. So the programming model was great. The way it was implemented is problematic, at least for some microservice architectures, so we wanted to address that. We recognize there has to be a better way. So we had a list of goals, we had an understanding of what's keeping us from accomplishing those goals, and all of that together helped us start building the Micronaut framework. So Micronaut has been designed specifically with microservices in mind, and it's being optimized specifically for building microservices. So folks will definitely build monoliths with Micronaut, and that's fine. And people will continue to build microservices with Grails and continue to have success with that, and that's fine as well. But both of those are examples of using a technology that really wasn't designed for that solution. So Micronaut can definitely be used for building monoliths, but we're prioritizing microservices. And one of the things that means is as we're confronted with design decisions, and maybe there's a couple of multiple ways we might solve a particular problem, and one solution favors microservices but comes at a cost if you're building a monolith, or a different solution might invert that and favor the monolith at a cost to microservices. As we're confronted with those kind of design decisions, we're absolutely prioritizing microservices. So the framework is being designed for microservices and is being optimized for that kind of application. The runtime is really lightweight runtime, and the runtime that exists today is based on Netty. Not Jetty with a J, but Netty with an N, totally different technology. So the runtime in Micronaut is built on Netty, and that enables us to have this really fast, flexible, lightweight runtime that doesn't require a lot of memory. And there are lots of these, but this is one of the things that's fundamentally different between the way that Micronaut has been put together and the way Grails was put together. So Grails, every single Grails application ever, there's never been an exception to this. Every single Grails application runs in a servlet container, and that's the only way to run a Grails application. Even if you're building an executable jar and executing that, it's still running in a servlet container. What we're doing is we're putting an embedded Tomcat inside of that executable jar. Every Grails application runs in a servlet container. There's no other way to run a Grails app. And we didn't want that same kind of relationship or limitation with Micronaut. So what we've done with Micronaut is kept the runtime separate from the rest of the framework. So we've built a runtime based on Netty, and that's the only runtime that exists today. But we'll build a gRPC runtime and maybe build other runtimes in the future if some a similar contraption like Netty comes along in the future, and there's good reason to want to have a Micronaut support for that. The fact that we've kept the runtime separate from the rest of the framework puts us in a position to build other runtimes in the future, which is great. And Micronaut is not just one thing. It's really a bunch of components. A couple of those components are, we've got a really sophisticated and interesting aspect-oriented programming engine. We've got a really interesting dependency injection container, and I'm going to demonstrate some of the interesting aspects of the DI container. But I'll start by saying one of the interesting things about these, the AOP engine and the DI container and other aspects of Micronaut, one of the interesting aspects of these things is we're not using any runtime reflection anywhere. So all of our annotation processing is done at compile time. There's no runtime reflection in the framework. So more on that when we start looking at some samples, and I'll clarify some points around that I think are interesting. In addition to an AOP engine and a DI container, Micronaut contains an HTTP client as well as an HTTP server. Remember that the framework is being designed specifically for building microservices, right? And in a microservice architecture, there's not one thing, there's a group of things, and lots of those things are communicating with each other, right? So something sends a request into the system, maybe to component A, and then component A calls component B, and component B calls component C. So you've got this graph of stuff out there where all these small processes are communicating with each other. In every one of those communications, there's a client and a server, right? When A calls B, A is a client and B is a server. And then if B calls C as a result of that, B becomes a client at that point, and C is the server for that particular communication. So lots of the elements in this architecture will be both clients and servers. So Micronaut recognizes that, and we've got this really sophisticated HTTP client that, again, I'll demonstrate in just a little bit, but there's some really interesting characteristics that the HTTP client has. So let's start with some demos, or take a step and take a look at some demos. So I'm going to start by building a really simple Hello World kind of Micronaut app, and even that simple Hello World app is going to enable us to do some interesting things, and then we'll take a look at this device up here. I'll talk about more in just a few minutes, and that'll help me demonstrate some interesting client-side load balancing stuff. Well, let's do this. Let's go jump out to the command line here, and I'm going to create a brand new directory here called ATL for Atlanta, of course. And I'm going to create a new Micronaut app. I'm going to add a couple of features to this app. I'm going to use Spock, and I want to use Discovery Console. I'll talk about why each of those, why I want both of those in just a minute. And I'll call the app AJUG Demo. All right, so that's going to create a brand new Micronaut app with the feature Spock and Discovery Console configured in that app. So let's open that project up in the IDE here. There's ATL, AJUG demo. There we go. And there's no support in IntelliJ yet for Micronaut, but we're still going to be able to use IntelliJ to build and work with Micronaut. I do it every day. One of the key pieces of that is when I created this application, what happened, if we look in the AJUG demo, you see there are Gradle build files here. So we build by default, we generate a Gradle build, and the IDE knows about Gradle, so it can load up all the dependencies and go about its business and do most of what it needs to do just by the fact that we're using Gradle. You don't have to use Gradle. There's a command line switch. You can say --build Maven, and instead of generating a Gradle build, we'll build a Maven build. So we're not coupled to Gradle, but Gradle is, we generate a Gradle build by default. We're working on really great support for IntelliJ for building Micronaut apps. None of that has been developed and released just yet. One issue that you've got to be aware of right now if you're using IntelliJ to do Micronaut development is Micronaut relies heavily on annotation processors. So I need to enable annotation processors in the IDE, otherwise a lot of the stuff in Micronaut won't work. Once the IntelliJ IDEA support for Micronaut is released, when you open a Micronaut project, we'll recognize that it's a Micronaut project, and a bunch of Micronaut-y things will become enabled, and we'll enable annotation processors by default. But be aware right now, if you start tinkering with Micronaut in IntelliJ, you're going to want to enable annotation processing, and we're going to see examples of why we need that, but we do need that. All right, so I've got a mostly empty Micronaut project here. And what I want to do is I want to create a new controller that I'll simply call Hello Controller. And I'll annotate this class with @controller. And so there's our first look at a Micronaut annotation. So it's io.micronaut. You see the package up there, controller. And remember that all of our annotation processing is done at compile time. So no runtime reflection is being done. At compile time, we're recognizing that this class is marked with @controller, and then all the controller-y stuff that needs to happen, all that logic gets generated at compile time. No runtime reflection is needed. So I'll add a method here that looks something like this. And I'll annotate this like that. All right. Super simple stuff we'll start with. And I'm going to go ahead and start the application up. And just like the controller annotation is dealt with at compile time, so is every annotation we're going to see and every annotation that Micronaut supports. It's all of our annotation processing is rigged up at compile time. So I'm going to work with Java because we're at the Java user group, and it's probably the language that has the most sort of familiarity in the room. But I'll mention that Micronaut is a polyglot framework, so we've got support for Java, Groovy, and Kotlin. And all the annotations that we support for any of the languages, we support for all of them. So I could write a Kotlin class and use these exact same annotations. I can write a Groovy class, use the exact same annotations. I can mix and match them. I can have an app that's using Java and Kotlin, or Kotlin and Groovy, or all three of them, or any combination of those. I'm going to stick with Java for the reason that I cited there. Okay, so I've got the application running. I want to, so let's send a request to the application. That looks like that worked. So this was the response. Everything before the A is what's in the response. Everything after starting with that's my command prompt. So hello Jeff is what was in the response. So if I say Jeffrey, you say hello Jeffrey, right? So what's happening is I'm sending a request to /hello/something, and that request is being handled by this method. Because hello/something matches this URI pattern here, and you can use these variable tokens. So the word name inside of curly braces there tells the framework that whatever is specified in that last part of the URL will be passed. That value will be passed as an argument into this method. And I'm going to keep this method super duper simple. We're just going to have it accept strings and return strings. There's lots of interesting stuff we could do inside of the controller with JSON and data binding and validation. There's a lot of different directions we could go. I want to keep the inputs and outputs here simple to focus on some other stuff that I think is compelling and what I want to focus on here. All right, so we've got a really simple controller that supports requests being sent, get requests being sent to /hello/something. All right, let's stop that app for a moment. And I'm going to write a test, and that test is going to allow us to explore some interesting capabilities of the framework. So I'm going to write this test in Spock. I'll call it hello controller spec. How many of you are familiar with Spock? Yeah, so more than 2/3 probably. Spock is a super terrific testing framework. You don't have to use Spock to test Micronaut apps. You can use JUnit. You can really use any testing framework. Spock has a bunch of really interesting characteristics. I'm a big fan of the Spock framework. So I'm going to use Spock for this example here. So let's get some stuff generated in this test. And I've got a couple of code snippets saved just to keep you from watching me have to type all this stuff out. All right, and we're going to understand what all that does before we're done. And likewise, we'll understand what this is all about before we're done. All right, let's see. Let's run this test and see if we want to see the test pass. And so while that's starting up, on line 14, what's happening there is we're starting up the whole Micronaut application. So we're not really running in a test environment. I mean, we are, but in the testing environment, we're starting up the real application. There's no mocking, there's no stuff. We're starting up the real server. So everything in the application is being started up when line 14 executes. And what's returned from that call to application context.run is a reference to the embedded server. That's the server that represents the application that's running. And one of the things that I can retrieve from that server is the URL that it's running on. And right now, when I run the application, that test passed, by the way. When I run the application is going to start up on port 8080. And I see something printed to the console to that effect. Also, notice that we see the startup time here is 965 milliseconds. And the app is doing some interesting stuff. It's actually registering with a service discovery engine that we'll talk about in a minute. So that accounts for some of that time there. So we've got really fast startup time. But the application is starting up on port 8080 right now. And I'm going to edit the default generated config file and add a property called micronaut.server.port and assign it a value of -1. And so if I wanted to specify that I want the thing to start on port 8086, I can do that. Now the next time I run it, it should start on port 8086. Where's it? Yeah, there it is right there, 8086. So you can specify a port number, but often what you're going to want for your microservices is you're going to want the thing to start on a random port. And the way to cause that to happen is set micronaut.server.port to be equal to -1. So there we go. The service started on port 49794. The next time I run it, it will almost certainly start on a different port. So what this line is doing is creating an HTTP client that points to the server that was started on line 14. And we don't know what port number the thing is running on, and we don't have to care, right? We have to discover that dynamically at runtime. And that's what embedded server.url will include. It'll be localhost : and then some port number. So on line 14, we're starting up the server. And on line 17, we're creating an HTTP client for making calls into that server. And line 21 is where we're making that call. And this is kind of the long, tedious way to do this. So this is one of the things we're going to evolve over the next 5 or 10 minutes is what will make that more simple and take advantage of some really cool features of Micronaut in order to do that. But the HTTP client that's returned from http-client.create is a non-blocking HTTP client, which in your real application might be what you want, right? You might want to make non-blocking calls to other services. But in our test, we need that to be a blocking call because I want to make the call, I want to get the results right now, and I want to make a claim about whatever was in the results. So that's why I'm calling client.toBlocking, and then the retrieve is sending a GET request to /hello/Jeff, and all of that whole expression evaluates to whatever was in the body of the response. So we see, hello, Jeff. All right, let's go back to our controller, and let's imagine that this is some complexity. There's business logic here that I want to get out of my controller and put someplace else. So let's create a helper class that I'll call message helper, right? And I'll put a method in this class. Doesn't really matter what the method is called. I'll call it create greeting because that's what it's going to do. And I'll have it return a slightly different greeting than what we had in the controller. I'll say hello there plus name, right? And I'm going to annotate this class with @singleton. And notice that's not a Micronaut annotation. That's the JSR 330 annotation, javax.inject.singleton. Our dependency injection container is not what I'm going to explore right here. Is we're going to look at the first few bits of some capabilities that the DI container supports. But I want to point out that our DI container is a fully robust dependency injection container. It's not just enough of a DI container to do what Micronaut needs. It's a full dependency injection container. It's fully compliant with JSR 330. It passes the full TCK, the Technology Compatibility Kit, so it is a JSR 330 dependency injection container. And it's an aspect of the framework, it's an aspect of Micronaut that can be used outside of Micronaut. So our dependency injection container is a standalone thing that can be used in any JVM app. You wouldn't even have to be building a Micronaut app. You can be just writing a standard Java app with maybe not using any other frameworks, but you want a dependency injection container. Our DI container can be used separate from the rest of Micronaut. We have examples and guides that describe how to do all that. So our DI container is compliant with JSR 330, so we use the JSR 330 annotations. So this tells the framework that I want message helper to be a bean in the Micronaut application context. And then in any other bean, I can inject that thing by, one way I can do it is I can use constructor-based injection. So if I declare that this constructor accepts a message helper as a parameter, then Micronaut will recognize that, and when the framework creates this controller, it will pass the message helper as an argument to the constructor. That by itself doesn't seem novel, right? So Juice can do that, Spring can do that, Grails can do that. That's how dependency injection containers work. But one of the interesting and valuable things to note is that we're not doing reflection to figure that out. At compile time, we're recognizing that this constructor is here and generating the instructions at compile time that know that when I create a controller, a hello controller, that before I do that, I've got to create the message helper bean and pass it as an argument to the constructor here. So the code doesn't look radically different than what, say, Spring or Grails or Juice developers might be familiar with, but the implementation is very different in ways that are valuable, right? So let's take advantage of that thing down here. So now I'm delegating to that helper. So that, again, remember that what we're doing is we're getting some complexity, some business logic out of this controller, and we moved it someplace else, and now we're injecting that helper into this controller. I should have just, this test should be broken now, because the test expects the return value to be hello, Jeff, but it should be hello there, Jeff, if our greeting helper really is being injected where I said it was. And the test failed. We expected this, but we actually got that. So we'll fix this, right? Change our expectation to expect to get hello there, Jeff, and I'll run the test again. And one of the things that I'll point out about what's happening in this test is I'm starting up the whole server, just like I described before, and the test runs really, really fast. This is an example of startup time for the application affecting the way that you build the application, right? So often, there are, let's say for our purposes, there are two kinds of tests. There are unit tests and there's functional tests. And in our unit test, you write, most of you know what unit tests are, right? You're writing a test for a particular component, and for a functional test, you're testing maybe the whole application. And functional tests are more expensive than unit tests because you have to spin up this whole environment. So as much as you can, you want to write unit tests, and then integration or write functional tests for the things that really need to exercise the whole stack of stuff. But doing that is expensive for a lot of applications, and that's the case with frameworks like Grails. But because the startup time is so fast in Micronaut, it's totally practical to just start up the whole environment, because the whole server starts up really, really quickly. So that's an example of startup time affecting how you do development. All right, so that test passed, and what I want to do is I want to add a constructor to our message helper and have it accept the embedded server, that same embedded server that we saw referenced in the test, as a constructor parameter. So I'm telling Micronaut now that when the message helper is created, it expects the embedded server to be passed as a constructor argument. And the reason I want that is so I can do this. From port number, right? So I can ask the embedded server what port number it's running on. And I want to make that part of the message here. We'll see why I want that in a moment. So now the greeting is going to be hello there, something from port number something. All right, so we should have just broken our test again. We'll run the test again, and we expect the return value to be hello there, Jeff, but it's actually going to be hello there from something or other, right? It's going to be that. So we could change the expectation to say, instead of expecting hello there, Jeff, maybe I could expect whatever's returned to start with hello there, Jeff. I could do something like that, but that's not what I'm going to do. Let's do this. Let's write an interface called greeting client, and I'm going to annotate this interface with a Micronaut annotation called @client, like that, and we'll say greet. What do I want here? I want @get. We're going to make all that make sense before I'm done, I promise. A little bit more to change here. I want to do that. We want embedded server, .application context, .get being that. And then down here, I want to get rid of all of that. All right, now let's figure out what's going on. One, let's run the test. And it should fail for the same reason that it failed before. Client.greet is going to return hello there, Jeff, from some port number. Let's make sure it failed for the reason we expected. Yep, so that's what we actually got back. So this appears to be doing what was happening before. So one way to make this test pass is I'm going to do this. I'm going to say when I call greet and pass Jeff as a parameter, what I expect to be returned is whatever I get back when I call greet and pass Jeff as a parameter. Right? That seems like a truism, seems like a reasonable enough expectation, but we're going to break that in an interesting way before we're done here, and that's going to help us appreciate some cool capabilities in the framework. So now what happened is we called client.greet, and the return value was hello there, Jeff, from port number something. And then we made the exact same call again, and that returned the same thing, so the expectation passed there. But as I said, we're going to make that fail, and it's going to fail in an interesting way before we're done here. But what I just did was I'm taking advantage of Micronaut's HTTP client. So the way to write an HTTP client in Micronaut, and I'm doing this in the context of a test, but you would do the exact same thing in your app, right? If you wanted to write, if you wanted to take advantage of our client to call some other service, this is how you would do it. This just happens to be in the context of a test. So you write an interface and annotate the interface with @client. And for now, I'm going to put a slash here. And what that slash means is this client will be associated with whatever server created the client. So I'll come back to that, but stand by on that. And I can have any number of methods in this interface. I've just got one here. And I've annotated that method with the same get annotation that I am using in our controller and specifying a URI there. And what's going to happen when I invoke this greet method is the HTTP client is going to send a request to this URI, right? So it's doing all the HTTP stuff. It's doing all the JSON marshalling. We're not doing any JSON stuff here, but if I accepted a parameter that was not a basic type, but was, say, a person, and a person has a first name, a last name, and an address has a city, street, state, and zip. If I passed an address, then that address gets marshaled to JSON, and that becomes the body of the request. There's a whole bunch of cool JSON content negotiation stuff that goes on. Again, I'm going to focus on strings for the reason I described earlier. So when I call this greet method, all the HTTP stuff is happening. The HTTP call is sent someplace. We get back a response. Maybe there's some unmarshalling that goes on. And eventually what's returned is whatever's in the body of the response. Notice that I've only written an interface. I haven't written a class that implements this interface. I've only written the interface. And what's happening, again, I keep saying it at compile time. At compile time, we're creating a class that implements this interface, and it has the greet method in it, and inside of that method is all the HTTP stuff, right? And an instance of that class is added to the application context when the application is started up. So what I'm doing now on line 19, instead of calling HTTP client.create, I'm retrieving the greeting client bean from the DI container, from the application context, and what's returned is something that implements this interface, and it's not a dynamic proxy. It's an instance of some class that we created at compile time. And now when I invoke this greet method, a bunch of interesting stuff is happening in not just the HTTP call, but other stuff, and I'll be able to talk about a little bit of that as we press along here. So watch this. So I'm going to change this to be AJUG demo. Instead of a slash there, I want AJUG demo. And what I'm going to do is I want to start up several instances of the application. So that's going to start one. This is going to start one. And I'll start one more. So now I'm going to have 3 instances of the application running. Remember, when I created the application, I specified one of the features I wanted was Discovery Console. And Console is a service discovery engine that Micronaut has support for. We support other service discovery engines. I'm going to demonstrate Console in particular. But because I specified that I wanted this feature added to the app, a couple of things happened. One is some dependencies were added to our build.gradle file, right? So this wouldn't have been there otherwise. If I created the project without having specified that feature, and I wanted to add this after the fact, I can definitely do that. I just add the dependencies to the build file. And in addition to the dependencies being added to the build file at application creation time, some config was generated for us. So this config that's highlighted wouldn't have been there had I not specified I wanted to use Discovery Console. So Console does a bunch of stuff, and I'm not going to go down the Console path right now. We're going to use some very basic capabilities that Console has to offer. And for those purposes, just think of Console, it's just a service discovery thing. And so when a program starts up, it can register itself with Console and say, okay, my name is this is the machine I'm running on, and here's the port number I'm running on. Service discovery is an important part of microservice architectures because you've got all these things running out in the environment. They need to be able to find each other, and service discovery is a way to do that. So what's happening, if you notice, this last line of output is registered service AJUG demo with Console. So every one of these registered themselves with Console. And in order to register themselves with Console, the program has to know where Console is running. And I happen to have Console running on my machine right now on localhost on port 8500, which is the default port for Console. So this console.client.default zone property tells the framework where your Console instance is running. If you have a Console host environment variable set, we'll recognize that, and that'll be used as the machine name. And if you have a Console port environment variable set, we'll recognize that and use that. And what's after the colon in each of these cases is a default value to use if those environment variables are not set. And I don't have Console host and Console port set, so the value of Console client default zone is localhost 8500. So let's go look at my Console instance right now. As I said, I have Console running on port 8500. And why won't that scroll? There we go. So AJUG demo, that's not what I wanted to do. AJUG demo, you see there, that's the application that we're developing. And you see the number 6 here. Half of those are health check nodes. So because I started up 3 instances of the app, we see 6 there. So if I kill these apps, I just killed all 3 of them. We'll refresh this. AJUG demo is gone. We'll start them back up. Run, run, and run. One of them is up, the other one's up. So now all 3 of them are up. So what's happening is when the service starts up, it's registering itself with Console and says, here's my name, here's where I'm running, here's my port number. So now other things in the architecture can go to Console and say, hey, where are the AJUG demos? And Console will say, hey, there's 3 of them. These are the machine names they're running on, these are the port numbers, and right now they all happen to be running on localhost, but wouldn't have to be that way, right? Something could reach out to this Console and discover all the AJUG demos that are running in our environment. So let's go back to our test.
Can you expand the AJUG demo?
Say that one more time.
Can you expand the AJUG demo
This right here? So I don't want to get too far down the path of exploring console. So there's information you can discover about the node. You can discover what port it's on. There's a bunch of stuff we can do there, but that's not where I want to. I want to press into some Micronaut features if we can do that. All right. So now if I run this test, we should have just broken the test. I expect the test to be broken now in an interesting way. And it is broken. Let's see what happened. So this says we expected something 41522, but we actually got something 24996. I'm calling the exact same method on the same object and passing the same parameter and somehow getting different results from each of those calls. And what's really happening inside of the HTTP client is not only the service discovery is happening, but there's some automatic round robining that's happening. So what's happened is the HTTP client reached out to console and discovered that there were 3 instances running. It discovered however many there are. And now the client knows about all those instances. And the first time I call greet, it will communicate with one of those instances. The next time I call greet, it'll interact with another one, and it'll round robin through all of them. And this is our application code, right? This is what your application code looks like for calling that remote service. So the load balancing is happening for us, the service discovery is happening for us, all the JSON marshalling is happening for us, and we're left with very, very simple code to look at. We don't have try-catch logic, we're not doing any of the retry stuff. The retry logic is, the round robining part of that retry logic anyway, is happening automatically, and that's why this test is failing, is there are multiple instances, and we're round robining through them. So I want to pause for just a minute, and we're going to press into that even a little bit more and find some more interesting things. But are there questions or comments about any of that so far? Right here.
Are you also generating a circuit breaker?
No, but we've got support for that. So there's a circuit breaker annotation. You can introduce circuit breaker support. You also get another interesting thing you can do is you can write a class called anything. And have that class implement your HTTP client interface. So you'll have to have an implementation of whatever methods are in that interface. And if you annotate this class with @fallback, that's all you have to do. You never mention the class anyplace else. What will happen is that thing, the HTTP client, will now use this as a fallback if it can't communicate with any of the remote services. So we've got really slick fallback stuff. We've got circuit breaker support. We've got some retry logic that I want to press into next and demonstrate. Yeah.
What about does it work together with a container like Docker, or is it completely separate from that?
Both. It works with Docker, so we publish Docker apps all the time, and it's completely separate from that. So you definitely don't have to use Docker. You don't have to containerize your Micronaut apps. But it works great, right? So really, when you build your Micronaut app, what you end up with is an executable jar. So you can put that in a Docker container. It's super simple to do, and we have lots of examples that do that. But you definitely don't have to do that. It's super simple to do that, and lots of folks are going to want to do that.
Is it compatible with Kubernetes or also?
It is. So we've got great Kubernetes support. So it seems like everybody's just reading through the user guide right now and pointing out sections in the user guide. We've got great support for Kubernetes, absolutely. Yep.
What's a realistic heap size for a service that does something?
Yeah. Well, it depends on what the something is. So if the something allocates 2 gig of stuff on every request, then a reasonable amount of heap is 2 gig. But really, I think what you're asking is for a real Micronaut app, what are you probably going to end up allocating for memory size? You can run real Micronaut apps. You can run a Hello World app in as little as like 10 meg of heap. The application could be doing a lot and still not require much heap. Depends on what the application is doing. So don't relate doing stuff with needing memory, right? You'll need some memory, but realistically speaking, real services might be deployed in as little as 16 meg of heap. 32 meg is pretty big. It's totally practical to run Micronaut apps in 16 meg of heap. So I've got a set of services running right now that are doing non-trivial stuff deployed out on GCP to support some internal stuff at OCI. And when I set those VMs up, I didn't want to take time to go through the sizing exercise. So I just allocated 32 meg to each of the VMs because I knew I wouldn't have to worry about it. And those services have never gotten above 16 meg. And they're doing somewhat substantial stuff. So of course it depends on what you're doing, but that puts you in the ballpark, hopefully. All right, one more. Yep, go right ahead.
Can you go back to your test case? You said that it was starting up the full app.
It is.
Is that per test class or for each test method?
Yeah, so the way this, well, neither. The way this is written per test class, not for, maybe that's what you said the first time. So if I had two test classes that look just like this, then I'd be starting 2 separate instances. But once per test class. So Spock has a feature called that annotation at shared there is a Spockism, and that tells Spock to reuse that variable for all the test methods that are in this class. So if I had 100 test methods in this class, we're still only starting the server once. I'm not demonstrating any of it here, but there's a whole Micronaut testing framework where you can annotate your test with @Micronaut test, and now you don't even need that code. It just happens, and we can share the instance across your test classes. There's cool stuff in the Micronaut test framework as well. But the way this is written right now, all the test methods in this class will share that instance of the server. There's only one test method, but there could be 100. They would all share that instance of the server. And if I had another test class that was doing the same thing, it's not sharing this server. Yep.
So at client on line 29, the annotation
Right?
is saying what? That go to console and look it up?
It's not saying go to console and look it up. It's saying that this interface represents an HTTP client. So a couple of things about that. Remember what I started with was I had a slash there. So there's no service discovery involved. The client will be associated with the server that started the thing. But even when I put a service name there, that still doesn't say go look at console. That says use whatever service discovery engine is configured in this project. So we've got support for console, we've got support for Eureka, we'll have support for others in the future. So that doesn't say anything about console. So that exact same code could be using Eureka had I added the Eureka dependencies to this project instead of console. All right, let me, all great questions, but let me press on and introduce a couple more things, and we'll open it back up, and I'm happy to address all the questions that folks might have. But let's press on for the moment. All right, so we've got a simple controller. That might be verbatim what I just wrote. It's pretty close anyway. We've got a simple controller that is annotated with that controller, and we've got one public method here that's annotated with @get. And by the way, that URI that I'm specifying with @get is relative to the path that's specified in the controller annotation. So if that up at the top there, if that said @controller/Jeff, then the URI for accessing this thing would be /Jeff/hello/something, right? So I've got slash up at the top. All the URIs that are associated with each of these methods are relative to whatever path is specified on the controller annotation. Remember that Micronaut is a polyglot framework, so I can have a controller written in Java, I can have a controller written in Groovy, I can have a controller written in Kotlin, and we're using all the same annotations. And you can mix and match them. You have to add the corresponding dependencies to your build file. So if we go take a quick look at the build file here, we'll see someplace right there it is. The inject Java annotation processor dependency. If I wanted to use Groovy, then I would have another one of those that would use the inject Groovy dependency, and the same with Kotlin. So you have to have the corresponding dependencies in your build, but you can use any or all three of those languages in the project. All right, I want to demonstrate some interesting stuff here. So what I've got here is the Micronaut base station. Let's see if I can do this without unplugging anything. So what I've got is there are 4 Raspberry Pis here. So I've got there are 2 big Raspberry Pis. These are Pi 3s. I think they're 3B pluses. And these are all 0Ws, Pi 0Ws. These have a half a gig of RAM on them, and these have a gig of RAM on them. So I've got 6 devices here. And this diagram represents, kind of describes at a high level what's going on here. So on one of these devices, I've got a home controller. We're going to look at the source code for this, and we're going to see some interesting things that the app does. But I've got the home controller running on one of these devices, and one of the big devices, and the 4 small devices are running separate instances of the exact same service. So that's the company service that you see spread across near the bottom there. So there's redundant. I've got 4 different instances of that service running down here. And what's happening is each of these is registering with console which is running on one of the other devices. So the home controller is dynamically discovering all of these, all the instances of the company controller. I'm going to come back to that and do something with that in a moment. But let's take a look at what the application looks like in the browser. So what I've got is a Vue.js front end here. It's a very, very simple front end. And when I loaded this page, what happened is a request was sent to the home controller, and the home controller, like would happen in a real microservice architecture, is reaching out to other services, right? So the 4 small devices are running company services that know how to return this list of companies that you see here: OCI, Moog, and Tesla. And this text right here is really the interesting part. So what's represented there is that indicates which of the small devices actually handled this request. So they're called MNPy1, MNPy2, MNPy3, and MNPy4. And each time I reload this page, what we should see is a different backend instance. Am I still connected there? I am. What's happening there? Let me get this page to reload. I hope I didn't just unplug one of those. If I did, we'll get it back operational here in a moment. Let's look out here. None of those services are running right now. Did I unplug it? Those guys look good. What happened there? Got to unplug the whole thing and restart it. While that thing is restarting, let's take a look at the source code, and then I'll be able to jump back into the application and show some interesting stuff that's going on there. So here is the home controller. There's only one of these, and this is what the Vue.js application is communicating with. And this is really the only endpoint that I'm going to demonstrate. So there's an endpoint here that is /companies. And what happens when you send a request to that to the endpoint is we're calling company client.getCompanies. And company client is injected as a constructor parameter here. And if we go look at company client, it's an HTTP client, right? So it's an interface that's annotated with @client companies. So what's happening, the small devices are coming up and registering themselves with console under the name companies. In the code that we're looking at now, we're in the home controller, not the company services. In the home controller project, we've got an HTTP client that knows how to go discover those company services. And when I interact with that by invoking the getCompanies method, a request is sent to /company. So that's reaching out to one of the backend services. Let's go back here. That's a call to one of these guys, right? The company services. And what's returned from that is all the data that, so what the company service is doing is sending a query to the database to retrieve all the companies, and that gets marshaled back to the home controller. If we go look at the company controller, now this is a whole different program. This is the program that's running on the small devices. When I send a request to /company, what's happening is this. And we're sending a query to the database to retrieve some company objects, and really the details here are not terribly important. But what's represented here is there's a backend service that sends a query to the database, gets some data back. That data is marshaled back to the program that called that, which is the home controller, and the results of that request get rendered in the browser. Let's see if we're back in action here yet. All right, so now the company services are up and running. We'll go back here and interact with the app. So this is a Vue.js app that is sending requests to the home controller program that's on one of the Raspberry Pis. And what the home controller is doing is sending requests to those backend services that it discovered dynamically. And this right there indicates which of the services handled that request. So each time I reload this page, you see that's changing. That request was handled by Pi1, Pi3, Pi4, Pi2, 1, 4. So the round robining is happening there. And this is where that's round robining is happening. From the home controller's perspective, we're just making a call to getCompanies, and the service discovery, the round robining stuff, that's all just happening. Now what I'm going to do is I'm going to unplug one of these. I just kicked that. I hope I didn't just unplug all of them again. So I'm definitely unplugged that one, right? So Pi2 is gone now. So it's either down for maintenance or it crashed, or for whatever reason, it's not running. And if we go back to our app and reload this, so that request was handled by Pi 4. The next request should be handled by either Pi 1 or Pi 3. What's happening here? Let me reload that. Something unusual is happening in the networking stuff. One failing is what I expect there. What's going on? Let me let that reload here. I'm not going to cycle the hardware again. If it doesn't come back to health, I'll describe what's going on, but something unusual is happening that surprises me. And I do this all the time, so I don't know what's going wrong there. Let's leave that there for a minute. But what should be happening, and what does happen, is when you call get companies, and so it's round robining through 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And when it gets to one that fails, what's happening is it automatically fails over to the next one. And again, I don't know what's wrong with the system there, but something's goofy in the environment. But when you make this call, remember what you're interacting with is the HTTP client that's discovered all 4 of these things, and it's round robining through them. And when one of them goes away, it might be the case that what you want to happen is you want to automatically retry the next one. And that's what this @retryable annotation does. So when you author the HTTP client, you get to decide if you want that client to automatically impose retry logic or not. And the way to express that you do want that is to annotate the interface with @retryable. And what that delay is about, so here it's set to 500 milliseconds, so half a second. So what's happening is the client is round robining 1, 2, 3, 4, 1, 2, 3, 4. Then I unplug number 2, 1 is successful, and then I try to make a call to number 2, and that call fails. So because I've annotated this thing with @retryable, we're automatically going to go try the next one, but we're going to wait that long before trying the next one. So you get to dial that. You can make that longer or shorter. I've got it set to half of a second right now. So when I tried to send a request to number 2 and that request failed, the thing would have paused for half a second and then went on to the next one. And as I said, something's goofy in the environment here that's keeping that from working, but I promise it really does do what I say it does, just doesn't right now, right? Does that idea make sense? Yep. In the back? Yep. Oh yeah, that's a thumbs up. Awesome. All right. So some numbers. I remember, so I mentioned some of the goals that we had were small memory footprints, small executable jar files, and fast startup times. So a whole world Micronaut jar is going to be about 8 megabytes, right? And then above that is going to be whatever code you put in the project, right? But that's pretty small overhead to bring the framework along, is what that 8 megabytes represents. Heap requirements, so you can run a Micronaut app in as little as about 10 megabytes of heap. If you're doing any real work, you're going to need some more than that, but that puts you in the ballpark, right? You're not talking about 500 meg, you're talking about probably 16 or something like that. So really pretty small memory requirements for the framework. Startup times around a second. Again, it depends on a number of factors, what else is going on the machine and things like that. But if we look at these that I just started up, that one started in under a second. This one started in 2 seconds. That's unusual. This one started in 1.7. So all 3 of those were starting at the same time. It was one of the factors. But typically you'll see startup times around a second, second and a half, sometimes less than a second. This particular application is registering itself with service discovery, so that's a factor there. But a second puts you in the ballpark. Not 30 seconds, a second, second and a half, something like that. And the absence of reflection is a big part of how we get there. If you profile the startup time for a Grails application and try to figure out where is that 20 or 30 seconds being spent, a whole lot of that time is being spent reflecting on your classes to discover annotations and things like that. So our dependency injection container and our AOP engine and all the proxies that the framework creates, they're all generated at compile time, no runtime reflection. With Groovy, we do that by way of AST transformations, and for Java, we do that by way of annotation processors. We also use annotation processors for Kotlin, using Kotlin's KAPT tool, which I think is pronounced CAPT. So the implementations are different, but the net effect, the result, is exactly the same for all 3 of those languages, and that is at compile time, we're recognizing the annotations and generating all the corresponding logic. So in the framework is a whole bunch of support for a whole bunch of stuff that's common in microservice architectures. So commonly, microservice architectures rely on service discovery. So we've got really great service discovery support in the framework. And while I'm talking, I just can't keep the back of my mind from worrying about what's going on here. I'm going to try that one more time, but I'm going to keep talking while I do that. I just control alt deleted that whole thing. So service discovery is a common thing that microservice architectures need. So we've got great support for service discovery in the framework, and I've demonstrated console, but we've got support for Eureka and can support others maybe in the future. If you're deploying your application on AWS, we've got great support for taking advantage of Amazon's configuration sharing stuff. And if you're deploying on GCP, we've got great support for taking advantage of Google services like the metadata server. And, so we've got support for all the major cloud environments. That config file we were looking at is a good example of that. So if we look at this application YAML file where I've got some stuff configured, I might have lots of things configured here. So the default file is called application.yaml. It's somewhat common to have different config files for different environments, right? So you don't need to configure GCP stuff when you're running in your development environment, as an example. So we've got support for environments that the framework knows about. So for example, in addition to application.yaml, you can have application-aws.yaml. And if the application is running on AWS, we'll recognize that and only load that file if we are running on AWS. And the same with application-GCP. And there's a list of environments that we've got great support for. But supporting these cloud environments is important because lots of folks are going to deploy their microservice architectures to cloud environments like GCP and AWS and so forth. Client-side load balancing is another great example of a capability that you really want in a microservice architecture. So Micronaut recognizes that, and we've got great client-side load balancing. We've got support for serverless computing. So it's really simple to write AWS Lambdas in Micronaut. We've got examples for how to do all that stuff. So Micronaut is not just this just a REST framework or just a microservice framework. It's a framework with support for all of these serious scale cloud services. So one of the questions that we're getting now routinely is the same question we were getting when we started building Grails, and that is, do we really need another one of these things? Because there are a lot of them out there. And Micronaut is really not just another HTTP server. In fact, it's not an HTTP server. We need an HTTP server, so that's why we built on top of Netty. But it's really not just another one of those. It's this really robust framework for building and deploying and managing microservices. And as I said, it's really not just another HTTP server. So we started work on this about a year ago. Memorial Day this year is when we released the first milestone. And that's when we open sourced the product. And then we released about a milestone a month for a few months after that. After Memorial Day, and then I think August is when we shipped the first release candidate. Just today Tuesday or Wednesday? Today is Tuesday. Today we released RC3, and RC3 is likely to be the last release candidate. So the plan is we're going to ship 1.0 next week, probably Tuesday. If it's not next Tuesday, we're very, very close. It's almost certainly going to be next Tuesday. So we're really excited about that. There are a bunch of resources out there already. Really all of these, if you go to micronaut.io, that's the starting point for all this stuff. You can navigate to the GitHub repo, the documentation, all of our guides. Micronaut.io is really the place to start. So let me take one more swing at this thing and see if things are operational here. So we've got 6 passing, right? So I expect one of them to be gone because it's right there. Let's go back over here. Pi 4 handled the first request. Pi 3 handled the second request. Now I can cycle through them. 431, 431, 431. Let's see. So let's unplug number 4. Fingers crossed. Number 4 is now gone. And the next request should be handled by 3, and it was. And then 1, And this request is going to wait that half a second. So we just tried number 4. Why isn't that failing over? There we go. I don't know what's happening in the UI there, but now we are cycling back and forth between number 1 and number 3. And so I won't go through the process. But if I plug this one in and we waited a moment for it to come back up and register, it really would start participating in the round robining. All that really does work. Never mind the demo demons that whatever just happened there. But that client-side load balancing is just, so the retry logic and the client-side load balancing are just 2 of the capabilities that the HTTP client has. There's a whole bunch more. It's all well documented. But I think that's one of the compelling features of the client. So let's open it back up for questions. Yep.
So you said no dependencies. Does that mean you implemented things like the JSON converters, the stuff that we today have to pull in, whether it's Jackson or Xerxes?
Can you repeat the question?
Yeah, so the question is, so I mentioned 0 dependencies. And does that mean that we have implementations for everything that you might want to do, like JSON marshalers and XML marshalers and ORM tools and all this stuff? So it doesn't mean that we've implemented all those things. It means that you don't need to pull any of those things in to a Micronaut app unless you're using them. So we do have, we are using Jackson for the JSON marshaling and unmarshaling if you're doing JSON stuff, which you're likely to do. But unlike a significant difference is if you create a Grails application and don't do anything to it, there's a ton of dependencies in there, right? You've got Spring, you've got all the Apache Commons stuff, you've got all the stuff that Spring depends upon. It's a very different approach, and that's a big part of the reason that you're able to get a Hello World jar file as small as 8 megabytes, right? So that's the overhead of the framework, and then what you add is what you add from there. Yep.
Given any thought to microservice orchestration?
What in particular about orchestration? The question is, have we given any thought to microservice orchestration? So do you have any specific aspects of that you're thinking about?
One issue I've run into frequently was that you have, let's say, the sequence of things that need to happen to external input, and then something fails in the middle. How do you recover from that? You can't roll back. You have to go on, but maybe you have to wait or something.
Yeah, so there's a lot to that. So one thing I can say about that is one of the things that the framework has great support for is distributed tracing, right? So we've got support for Zipkin and other distributed tracing engines. So one of the challenges associated with microservice architectures is you make a call into the thing, and the thing you called might call 3 other things, and each of them call 3 friends, and those call. So sometimes it's hard to reason about what all is happening when I create an account. Who all gets touched and what pieces are involved in that. And distributed tracing can help with that, right? You can visualize all the pieces of your architecture that any particular request is, any piece of the architecture that are invoked for a particular request. So we've got really great support for distributed tracing, and it's an annotation-based thing, so you can annotate an endpoint and say, okay, I want to start a span right here, and then all of the tedious distributed tracing stuff happens automatically without you having to write any of the Zipkin code or any of that stuff. Separate from that, from a programming perspective, when you're writing code that's going to call some remote service, and we'll go look at our home controller again as maybe an example of that. So right here, we've got very simple code, but what's happening there is not necessarily simple, right? So service discovery is happening, maybe retry logic is happening, maybe there's a circuit breaker, maybe there's fallback stuff in place. This code is kept really simple. What I want to happen if I can't communicate with that service, I get to decide what I want to do here. So if what I want to do is just round robin through all the instances that were discovered from service discovery, that's all I need to do, then this is how I would write the thing. I'd probably put the retriable annotation on the company client interface, but I might want to keep it just this simple. But I might not. Maybe what I want to do is I want to wrap this in a try-catch block and handle certain failure conditions and then handle them however I think is appropriate. Another thing I might want to do is I might want to put, we've got great support for HTTP filters. So you can write filters to get applied to every HTTP request that's outbound from your HTTP client. And in that filter, you can do whatever you want to do, right? So you can check the response, and if the response is a certain error code, now you're in your code. You get to do whatever you want to do in response to that. So there's no trigger, no one thing in the framework that says do this and we'll handle all of your orchestration for you, but you've got lots of options. Hopefully that makes sense.
I'll tell you what, we're all out of time on this, but there's 3 things before you go. 1, if you have questions, go ahead and ask away. But first off, I want to say thank you for coming.
Absolutely.